controls flow around the body by controlled changes in vessel diameter. Okay? Your body uses controlled changes in vessel diameter to direct flow around the body. So if there were a fill-in question on a test that says something along the lines of, your body uses controlled changes in blank to control flow around the body, you would put in there vessel diameter, radius of the vessel, something like that. That's the number one factor that your body uses. The other two don't normally change. Does the vessel length ordinarily change? No. Now there are times vessel length changes. Okay? There are a couple of instances that we need to be aware of. As you grow, okay, you get bigger and you age, your vessel length increases. Resistance increases as you age. The heart has to work harder as a result. Okay? But that's normal. Our body's set up for that. A bypass. Okay? If you have a bypass surgery and you put in a vessel to bypass around, say, an occluded anterior interventricular artery, well, they don't actually take the bypass out of the heart. They go over here to the subclavian and they take the bypass out of that and they run it down to the heart. And so they have to make sure they pick a vessel and shield it properly so it can handle that increased pressure. And then the third point is actually one that my brother-in-law, who's a nurse anesthetist, told me about, was actually on his boards and had to deal with this. And it's the idea of IV tubing. And I never actually thought of it before, but if you put an IV tube in somebody, that's essentially like adding a vessel. Okay. So you hang a bag of some solution to put it into somebody's vein, and that tubing is usually a fixed length. But let's say you got to do something a little bit different, and you have to put some more tubing in, or you move it farther away. If you increase the tubing length, what you've adjusted on that thing to adjust the drip rate coming in will no longer be accurate because the flow rate goes down. Okay? That's like increasing the vessel length. So whatever it's calibrated to, it's going to be inaccurate. So if you basically went like this, if you doubled the tubing length, what happens to the flow rate? And the answer is it's cut in half. Okay? So there are some practical applications to that. But ordinarily, vessel length is not going to change. Okay? How about viscosity? Viscosity of what are we talking about here? Blood. Okay. So this means the thickness of the blood. Do you think that changes much? Yeah, I got a yes. Okay. All right. What kind of things are going to change the viscosity of the blood? How hydrated you are. Yeah, that's the primary factor. Okay. Temperature. Your internal body temperature better not change much. If it change, plus or minus 3 degrees, you're going to be in a world of hurt. So that probably won't have a major factor. Sure, yeah. If you donate blood, then you've lost some red blood cells. So now here we have to kind of, right, okay. So we'll jump ahead a little bit to the next chapter. Blood is a connective tissue that's 55% liquid portion called plasma, 45% the solid portion called hematocrit. That's the cellular portion. Now, most of the thickness of blood is due to the hematocrit, the number of cells that you have in it. So yes, absolutely. If you donate blood, you're going to lose some of those red blood cells. The viscosity of your blood will temporarily go down. Definitely, without a doubt. Plasma, not so much, because plasma is mostly the water portion, and so as long as you hydrate, immediately, if you just donated plasma and didn't get anything back, yeah, it would. But I usually donate plasma a couple times a week, and they just very thoughtfully pump in some saline into you, and it doesn't cost you anything, and that doesn't change anything too much. You just have to hydrate after that. There is one other component here. The plasma also contains a lot of dissolved protein, and that protein is mostly a protein called albumin, which is synthesized by the liver. Okay, and that has a lot to do with the osmotic pressure of the blood, okay, and the viscosity. So really, liver function can contribute to the viscosity of the blood. And actually, we'll have a lot to say about that later. The liver synthesizes a protein called albumin, and albumin contributes significantly to the osmotic pressure and viscosity of the blood. So impeded liver function can actually lower the viscosity of the blood. Which on one hand sounds like that'd be great because it makes the heart work a little less hard, which is true, but it messes up our osmotic pressures in the flow. So we'll talk about liver malfunction a little bit. But yes, number one, guys, the thing that changes viscosity most often is the degree to which you are hydrated. Okay? If you are dehydrated, the blood becomes more viscous, And one of the things you see of somebody that's dehydrated is the heart is beating faster. They can become tachycardic as a result. And that is primarily because the heart has to beat harder to move this more viscous blood around the body. Okay. Oh, and of course that leaves the major factor, which is resistance. And that's the one that's controlled either reflexively or by sympathetic vasomotor tone. And I described that, didn't I already? I mentioned that in the medulla oblongata we have a center in there called the vasomotor tone center. Yes, no, maybe? Did I mention that? Okay, mention it? No. I know we went over a little bit the autonomic nervous system, and I quizzed you guys a little bit, so I know you remember the parasympathetic and sympathetic sides. When it comes to blood vessels, they are innervated by pretty much just the sympathetic side of the ANS. Okay? Blood vessels are innervated and controlled just by the sympathetic ANS control, not parasympathetic. So perhaps you remember from your study of the autonomic nervous system that most organs exhibit dual innervation, where they're innervated by both parasympathetic and sympathetic fibers, and that they have opposite effects usually. Blood vessels are just innervated by the sympathetic side. And so they release epinephrine. And we know that there should be then in blood vessels, there should be an adrenergic receptor. In this case, it's an alpha-1 adrenergic receptor. And it causes contraction of smooth muscle when it's activated. So that's my elaborate way of getting around to the point that says sympathetic stimulation to blood vessels causes vasoconstriction. Okay. Sympathetic stimulation to blood vessels causes vasoconstriction. What causes vasodilation? No, you weren't listening. I just said, I just said that blood vessels don't have dual innervations. All right? Which is why I asked the question. Okay? It is tricky. It has a question like that, yeah. Okay. So, the way you get a blood vessel to dilate is to decrease sympathetic stimulation. Okay? You decrease sympathetic stimulation, and then what makes it dilate is its own internal pressure. Okay? You got a pipe, and the pipe has some pressure in here. Now, we're constantly constricting the pipe a little bit. That's called vasomotor tone, or sympathetic tone. When we relax the sympathetic tone, in other words, we let the smooth muscle relax a little bit, the pressure in here is what makes it dilate. So it's always trying to dilate because there's pressure inside trying to stretch it. So we always keep it a little constricted. And when we relax that constriction, it dilates by itself due to the pressure generated by the heart. So we don't need a parasympathetic antagonist. That's accomplished by the internal pressure. Okay? So if I increase sympathetic stimulation to an organ, like say the stomach, what would I expect blood pressure or blood flow to the stomach to do? Decrease. Right? And it would decrease because the increased sympathetic stimulation to the heart, I didn't mean heart, stomach is what I said, increased sympathetic stimulation to the stomach, what happens to this number? What happens to the radius? Goes down, right? So that means resistance goes up. Resistance goes up, flow goes down. Got it? Okay, there's a fill-in section on the test where I ask you to do exactly that. Okay, it's what I call my Mad Lib question, where I kind of write out most of the dialogue and I leave some blanks out. Okay, and so it goes just like that. If I increase sympathetic stimulation to the, stomach, this would cause the radius of those blood vessels to, you would say, decrease, and then it would say which would cause the resistance in that area to increase, which would cause flow to the area to decrease. All right, that's what I expect you to be able to do. Okay. Now, I apologize for the fact that I goofed up heart a second ago when I said that, because the heart is interesting. The heart has the exact opposite response. Okay, sympathetic stimulation to the heart actually inhibits vasoconstriction. So the blood vessels in the heart will actually dilate as a result. Mm-hmm. Within the heart, and this is true of most muscle tissue, as a matter of fact, okay? Most skeletal and cardiac muscle. Sympathetic stimulation to those organs causes dilation. But that's the only exception. So let's take a few terms that they've got here for you. We know systolic and diastolic pressure, right? Been over that. Well, when you check the blood pressure out here in the extremities, the brachial artery is a pretty good estimate of your systolic pressure, but beyond that, then the pressures start to blend. And instead of being systolic and diastolic, we take an average of the two, and we call that mean arterial pressure. Mean arterial pressure. And you can see mean arterial pressure starts to decrease as you go farther away from the heart. So there's the aorta, it's still pretty darn high. Arteries, arterioles. By the time we get down to the capillaries, we're barely at 20. We're down into the veins, and we're about 10. By the time you get back to the vena cava, it's hardly higher than 0, about 3. So there are a couple of different types of pressures that we can calculate. The difference between our diastolic pressure and our systolic pressure, remember what that's called. I know there was a pre-lab or a quiz question about this. What's the difference between your diastolic and systolic called? It's called your pulse pressure. It's called your pulse pressure. Okay, so that's your pulse pressure. You can have what's called a widened pulse pressure, where that gap is larger than normal, usually because of an elevated systolic pressure. And then the way you calculate mean arterial pressure, remember that one? There's two different ways to do it. Well, the way I remember to do it is you take your systolic pressure and you double it. Okay. No, wait. Diastolic pressure and double it. And your systolic pressure, you add those three together and you divide by 3. Okay. So you take twice your diastolic plus your systolic and divide by 3. So you double your diastolic, add it to your systolic and divide by 3. The reason for the thirds there has to do with the cardiac cycle. The cardiac cycle spends 2/3 of the time in diastole. So it's not a simple average. Otherwise, you could just take the diastolic and systolic and you could take them and average them and you'd have it. But because it's not apportioned evenly, you have to, it's a weighted average is what it is. It's 2/3 diastolic, 1/3 systolic, which is the other way to calculate it. Okay. But it's easier if you just double the diastolic, add it to your systolic, and divide by 3. We got it? Okay. And that can be used diagnostically. Your different organs should have a different mean arterial pressure where it feeds into the organ, and that can be tested with a barometer. They can take a cannula and they can snake it through a blood vessel, and they can actually record the pressure going into the different organs and see if it varies from what it should be. That's called secondary hypertension. If you have high blood pressure at a particular organ, okay, that's not systemic hypertension. It's called secondary. It means it depends on that organ. So you could have, most often it's a congenital defect where there's a blood vessel anomaly, say going to the kidneys or to the liver. A horseshoe kidney is something that's fairly common, where the kidney, instead of being a discrete kidney, actually forms a bracket, and those tend to have restrictions in them, and so it causes secondary renal hypertension, and that can cause damage. And it won't show up in your regular blood pressure here. This blood pressure will be normal, but the kidney will be malfunctioning. Okay. And really, you're not going to do anything with mean arterial pressure. I'm not going to have you calculate. Well, I did on the quizzes, but I don't put that on the test. You do not have to calculate mean arterial pressure on the test. Okay. In fact, I don't give you any math calculations you have to do on this test. We'll do a few. Oh, is that a lie? Let me think. No. When we get to renal function, we'll do a few calculations, and we'll go back and look at cardiac output. Here, nothing new. Okay. I think this is the first section. It's going to get into talking about the angiotensin mechanism for regulating blood pressure. This whole thing. What figure is that? Figure 1910. Okay. So, good news. You don't have to know this right now. Okay. Let me just give you a framework. You